Hello everyone, my name is Rustem Islamov. I am intern in P-Rhetorics Optimization Lab. Today I would like to present our recent work with Shunkan and P-Rhetoric, distributed second-order methods with fast rates and compressed communication. Let me first give some brief motivation for our work. One of the most popular methods in distributed optimization are gradient-type methods. Such methods are investigated a lot in recent years, and they can probably benefit from compressed communication. However, the rates depend on the condition number, and it's hard to tune the step size for these algorithms. In addition to gradient-type methods, there are some local methods which have some additional problems like limited communication avoidance effect, for example. Our desire is to solve these issues. One of the possible solutions is to use second-order information about the objective. However, all existing second-order methods suffer from at least one of the following problems. Communication cost is too high, or rates depend on the condition number. Our goal is to develop a communication-efficient distributed Newton-type method whose local convergence rate is independent of the condition number. We consider L2 regularized problem, which has the form as on the slide. Here, each function is generalized linear model with new Lipschitz second derivative. For simplicity, we use the following notation. The local function is fi, and the whole function is capital F. Let's briefly look at standard Newton method. It has local quadratic convergence rate independent of the condition number, but the communication cost is too expensive. It is OD squared. Our first contribution is Newton star. The only difference with standard Newton method is that we use the Hessian at the optimum instead of the Hessian at current point. It means that each node computes only local gradient and broadcasts them to the master. We have proved local quadratic convergence rate for this algorithm. Here we assume that the Hessian at the optimum is lower bounded by mu star times identity matrix, and mu star plus regularization parameter lambda is positive. Let's briefly summarize the properties of this algorithm. It has local quadratic convergence rate independent of the condition number, cheap communication cost, but it has only the theoretical value since we do not know the Hessian at the optimum. Our next contribution is Newton learn. Our desire is to learn the Hessian at the optimum iteratively and do it effectively in terms of communication. We want to learn the second derivative of loss function at the optimum, but the update hk plus 1 minus hk should be sparse. In addition to that, local rate should be independent on the condition number. The learning scheme for HKs is inspired by Diana method. We perform Diana-like step and then project onto positive orthont. Here we use unbiased compression operator. The simplest examples of such compression operator is random specification. As you can see, learning step size eta depends only on the compression. We have proved local linear convergence rate for this algorithm for some Lyapunov function. As you can see, the rate doesn't depend on the condition number. It depends only on the compression. And we indeed learn the second derivative of loss function at the optimum. We have conducted some experiments on logistic regression problem, comparing our method with accelerated Diana, Dingo, and BFGS. As you can see from these numerical experiments, our method outperforms others by many orders in magnitude. We hope that this new approach is very promising and should be investigated. Thank you for your attention.